Today we are going to be talking about Ampere's law. Now, Ampere's law can be thought of as the magnetic analogy to Gauss's law. Recall Gauss's law was a way of finding the electrical field from a distributed charge, relying more on symmetry than on integrating Coulomb's law. Well, Ampere's law can be used to find magnetic field in a way that, if you have similar symmetry, can be much easier than integrating the Biot-Savart law. So first, the formula for Gauss's law. The integral of b dot ds is equal to mu sub naught I enclosed. So what do each of these mean? B, that is the magnetic field. ds represents a small infinitesimal step along a closed path. This is the dot product. Generally, it's easier to use if we have some path that we know is either directly in line with the magnetic field or is perpendicular to the magnetic field, but this equation does hold true for any. Now, this symbol right here means that we are integrating over a closed path, so we don't actually have boundaries like with a normal integral, but when we do the integration, sometimes we will put boundaries just that it starts and stops at the same place. Mu sub naught, that is, again, the permeability of free space. That's that 4 pi times 10 to the negative 7th Tesla meters per ampere. And I enclosed represents the total current enclosed by the loop. So much like Gauss's law referred only to the total enclosed charge, and there were cases where we could ignore some charges completely because they were outside of our Gaussian shell, we can sometimes ignore some currents completely because they are outside of our Amperian loop. So consider this diagram. We have three currents. I1 and I3 are coming out of the page, and I2 is going into the page. Applying Ampere's law to this loop, we would only include currents I1 and I2. Now, like with Gauss's law, this is something that with the proper application of calculus we could use in the general sense, but we are going to focus on a few cases that have some nice symmetry to them. So case number 1, we're trying to find the magnetic field around an infinite wire. Now recall we have already done this for the Biot-Savart law, so we already know what the answer should be. However, also recall, it was not that easy for the Biot-Savart law. We ended up having an integral that I ended up saying, the integral is this, just trust me on that. Well, doing an Ampere's law analysis of an infinite wire, we can see, okay, this is the cross-section of the wire. There is a current coming out of the page, and all of that current is constrained inside this, the cross-section of the wire. Because of the radial symmetry and because of the way magnetic fields work, we can reasonably assume that a circle surrounding the wire out to a distance r will have 1, constant magnetic field, and 2, a magnetic field that is always in the tangential direction, which means that B is always in the same direction as ds. The angle between them is 0, so that's just integral b ds. So since magnetic field is constant along this path, and since it's always at the same angle along this path, we can replace this integral with just b times the integral of ds, which is the total length of this path. This path is the circumference of the Amperian loop, which has a distance of 2 pi r. So this integral is equal to b times 2 pi r. Apply Ampere's law, that integral is also equal to mu sub naught I enclosed. We can then take this equation, rearrange, solve for b, get b is equal to mu sub naught over 2 pi times I over r, which is exactly what we got with the Biot-Savart law, but I think you'll agree this was much easier. Using Ampere's law will also let us look at situations that would have been a bit more difficult to solve for the Biot-Savart law. For example, what if we wanted to find the magnetic field inside a wire? Now this is analogous to trying to find the electric field inside a ball of charge. So we make our Amperian loop go inside the wire, and we recognize that not all of the current in the wire is inside that wire. So we say that the total current inside the wire, the I enclosed, is equal to the total amount of current times the ratio of this small area divided by the total area that all of the current is going through. And I have written that right here. I times pi r squared over pi big R squared. Little r is the radius of our Amperian loop, and so it's the radius of where we're looking for a magnetic field, and big R is the radius of the wire. Now you'll notice that these pi's can cancel. So with this formula, rearranging, solving again for B of R, we get that the magnetic field is equal to mu sub naught over 2 pi times I. This, by the way, is the total current, not the I enclosed, but the total current through the entire wire, times little r over big R squared. So as you get farther from the center of a wire, until you reach the edge, the magnetic field increases with distance. This is similar to how in a sphere of constant charge density, the electric field would increase until you reach the edge. Scenario number 3. What if we had an infinite sheet of wire? So there's two ways we can look at this. The first way is imagine that we do have a plane, like a plate of metal. And in that plate, current was all flowing in one direction. Now, if this plate were infinite, or at least very, very, very large, then we could say make an argument by symmetry that the magnetic field near the surface of that plate was reasonably constant, and perhaps depended only on how far away you were from the plate. So in that case, we could create an Amperian loop like this, where these two sides are a certain distance away from this plate. The magnetic field will be going in these directions, and there will be no magnetic field going into or out of the plate. Again, by symmetry, if it were, say, going in on this side, symmetry would require that it's also going in on this side, which can't be. Which means that when applying Ampere's law to this, this top side and this bottom side cancel out. And so the integral of b dot ds is equal to mu sub naught, or b dot ds is equal to 2 times the magnetic field at this distance times this height. So magnetic field times the height here, magnetic field times the height here. I enclosed, we need to use lambda to represent, this time, current density. So lambda before was linear charge density, now lambda is linear current density. And we can see that the longer or the higher this rectangle, the more current it's going to enclose. So the current is lambda times h, but we can see these two h's will cancel, and so the magnetic field near an infinite plane of current is equal to mu sub naught lambda over 2. Notice this does not actually depend on how far away you are from the plate. Like with the infinite plate of charge, the magnetic field near an infinite plate of current is constant, as long as you are close enough to the plate that you can reasonably call it infinite. Again, I would like to emphasize that the law of superposition still does apply. If we have multiple objects that are near each other, we can use Ampere's law on each object individually to find the magnetic field from that object, and then combine them to find the total magnetic field.